Okay, so I've decided to use this channel to try and attract work within machine learning and programming. The plan is to publish one video every week, at least for now, within that field. And unfortunately, this week's video turned out to be a little bit rough around the edges. But this was the first video I made, and hopefully it will be better next week. So the video is about a project with an inverted pendulum. So the pendulum is free hanging from a motorized arm attached to a cart, which is also motorized. And I've made a physical model which I'm using for logging data, which in turn I use to train a neural network, which will be a reinforcement learning environment later. Yeah, and now we can swap to the model and test it a little bit. So this is how it looks like. It can move back and forth. This bit you see here is actually an end stop, which will cut the power for direction, travel in that direction. And where it is now, it also is at the end stop. So it can move between this point and this point. And the control should try to keep it at an even more narrow movement. The colors is used for detecting positions. In the beginning, I started with using saddle point and some high-risk corner detection and various OpenCV techniques, and all Python through the project. It worked, but it was just too slow. So I started, and we are back. The panel you see is a simple TK Inter panel I made, just to have a GUI to operate the system. And now I put it in manual control, turn up the power a little bit. I have, these are the control buttons. That's M1 is for the swing, M2 is for the cart. I should probably write that in the GUI. So right now, let's see. Yeah, power is on, should work. Yeah, I can hear it moving. Now I swap to the other view. And I'm back. So I can demonstrate manual driving it. I can adjust the power, and I can also adjust how many 20 millisecond after each other. So this is pretty much maximum speed for the cart travel. And this is for the swing. The swing is more than fast enough. Adjust it down a little bit. So that's manual driving. And then I have my plan was to make a control neural network with a policy for how to control the system to stabilize the free swinging pendulum in an upright position. Now, I haven't gotten that far yet, but I also still have that inference mode here. On the inference I can choose, but I can also put the slider all the way up to 100% random, and then it will be moving in random for gathering data. Let's try that. Okay, actually now it's on in a special mode that I made, where it only moves the cart, and then every 40 seconds it starts moving the arm. And the reason for this I'll come back to later. So this is a simple hardware overview of the system. I use a Basler camera with a USB connection to the PC, and the PC processes the information, and well, right now it's just random movement, but with time it will be a control loop with a policy network trying to stabilize the pendulum. The PC communicates with an Arduino unit down here with the motor controller via Modbus TCP. It might not be the ideal protocol for this, but it seems to be working okay. And most Arduino examples I found was via router. I didn't want to use a router between the PC and the Arduino. Then it's hardwired signals to two motors, one for swing, one for cart travel. And then the position is fed back through these color patches again to the camera. The camera, first I tried using a PlayStation 4 camera because it is supposedly rated for 240 Hz, and some nice guys on the internet had made the driver so you can use it with the PC. I had it working, and first of all, I could not get it to work in a useful mode above 120 Hz, which is actually too slow for this project. And also there was a lot of other idiosyncrasies, so really that was just a waste of time. I wish I would have bought a more expensive camera sooner. The Basler camera is a high quality camera that operates at 620 Hz maximum. USB connection, and it comes with its own Pylon software. And including in the Pylon folder, there is a lot of examples, very good examples for the camera. Hard to find examples on the internet, but in that folder there is just lots and lots. Then it's fed back into the PC again, and we'll have a quick look at the software, how it is handled, first in a C++ part of the software, and then the position data is fed over to a C Python part of the software for further treatment. A quick overview of the software. Half of the software is C++ and half is Python. So now I start with the C++ part. There is a image collector running in its own thread. It collects images and puts it in a queue. Then there is the main loop, which collects that, receive that queue. And then it's the information, the frame is passed onward to the image processing. The image processing finds the color patches. First, it detects it scans the whole screen. It uses stride. It doesn't check every single pixel, but it scans the screen for first blue pixels, then green pixels, then red pixels, then yellow pixels. And it stores those location for those pixels, and then it starts checking for neighbors. And when it's found sufficient amount of neighbors with the corresponding color, it says I found the blue patch, for example. Then it finds the mean position of all the blue pixels, and that will be the position for the blue patch. So then it returns 5 locations for the patches. 1 blue, 1 red, 1 green, 2 yellow. That's sent back to the main loop. From the main, this is then passed onward to the C++ part. No, to Python. And first actually to a communicator, which also runs in its own thread. So all the information being passed, it's passed through queues. It's communicating with C++ via a localhost socket communication. The Python part will process. We'll get to the Python part, but it will use that position information to calculate the next command for the motors, and then the commands will also be sent back to the C++ for logging. And that's the last part of the C++ part of the code. The information of position and the commands for the motors is sent to a log, also in its own thread. Then it's back to collecting an image again. And from the picture is taken and until it's sent to Python, I haven't measured it exactly, but I know that the processing is way below 1 millisecond, and indication is that it's very fast. So from the picture is taken to a new command is sent, I know it's less than 5 milliseconds. And then a new picture is taken every 20 milliseconds. Or actually, the pictures are collected at 620 hertz. But it will be processed in the main and find the speed and the position, or it will be processed in main, and it's also processed at 620 hertz. That one runs at 620, and then it will be downsampled to 50 hertz. This way, I know for sure which direction it's traveling. I have set a minimum or a maximum amount of degrees that it can travel between each frame before I can no longer say with certainty which direction it's traveling. And I think it's like 50 degrees or something like that. And since that is being checked at 620 hertz, I don't have a problem with it skipping a frame. So then I have quite certain information at 50 hertz, which is then sent onwards to the Python. So the control loop itself is is operating at 50 Hz. So onwards to the Python part of the code. Okay, that also has the communicator is not running in its own thread. I started out with threads in Python, but I had a poor experience with it, and I decided to move away from threads. I have some separate processes, but I don't use threading. Okay, communicator gets info from C++ and send info back through socket communication. This is passed through the main, and it's all running in the same thread. The communication is not through queues, it's through just function calls. So it receives the position, and the plan is that it will be passed to a neural network. Actually, I have implemented it, but the neural network is not working quite yet. It's not good enough. A policy network which will tell the next move based on the current state. Then the command is sent back to the main. What else is there in the Python loop? Yeah, and then the commands will be sent back to C++, but it will also be sent to a Arduino communicator communicating with Modbus TCP. And this is just software, everything, but it will move out with the Ethernet port. And create command for the motors. It will be turned into voltage signal to the motors. And that is pretty much the whole code, except for one thing which I haven't added here yet, and that's the simulating part. And that will replace this whole communication part with a let's see if I can just remove this whole thing now. This whole thing will be removed and replaced with a simulator. And the simulator is a neural network which I have trained on the data which I logged. So from the current state, it will predict the next state, the next position of the cart, the arms, the pendulum. And that's where I'm at now. This simulator, this network, which is simulating, which I thought, it's working, but it's not working great. Next step will be to improve this simulator. this neural network, so it's working better. And then the step after that will be to use this as an environment, run reinforcement learning, DDPG, to be able to stabilize the pendulum in an upright position. Okay, so my original plan was to just log the data, log the position and the speed of cart and swinging arms, pendulum, and then offline I would use that log to train a neural network with just the behavior of the system. And then I would use that neural network and run a lot of simulation on it and find long strings of states which led up to the pendulum being in an upright position with low speed, pretty much right up, and ready to be stabilized up there. Then I will have all these state points starting from some low value to high value, and I will use all those states, the commands I use for those states, as ground truth to train another neural network, which would be the policy neural network. I had very little success with this. So right now, actually I had a tiny bit of success, but more on that later. But right now I would just gone away from that part and just focused on the system neural network, and that's what I want to demonstrate now, because that is starting to look okay, not great, but okay. So here you can see what the computer sees through the Basler camera with the processing done. The spots mark the detected position, the spots in the middle of the color patches, and you can see them dancing a little bit. It's not ideal. I could see if I can do something about that, and I will, but for now it's sufficiently accurate. Let's drive it around a little bit. Actually, I have been trying to adjust this. It has been more accurate. I adjusted it to get the green patch more accurate, but I can see I have lost accuracy on the blue patch, so I have to reverse what I've done. But for demonstration now it's okay. Let's turn up the power a little bit and I will run it a little faster. Slightly inaccurate, but it's not failing. I don't get an angle error, I see. Okay, so now I'm running the system in simulation mode. So instead of using that C++ part, which capture the position of the pendulum, I'm now using the behavior neural network to simulate the neural network which has been trained on log data. It's not working great, but it's not working too shabby either at the moment. So I put it in manual mode and start running it. Seconds. Okay, if you can perhaps here I'm also running the physical module on the side here. And it won't go any further than that. I'm going to turn off the power for the physical model because it's sending signals both to the simulator and the physical model. Okay, so it worked okay up to this position and then it just stopped. Then I tried the other position and it runs a lot better. You can see the outer arm, the pendulum is hanging pretty much straight down as it would be, so that's good. I turn up the power a little bit and now it's moving and it just falls down. That really doesn't happen in real life. Yeah, it's the way it is, and I'm looking to improve this model so I can use this model as an environment to train with DDPG. That is on my plan for next week. No, it's not on next week. Next week I'm just going to improve this model and improve the code so I can put the code on GitHub. I've just made myself a GitHub repo, a GitHub account, and the link is in the description, but there is nothing there. But I will put the code for this project during this week. Okay, so this system isn't working perfect. For example, if I try to run the cart back and forth, the inner arm here should not be affected at all. It won't be that in real life, but here it is affected. Okay, won't move at all. Okay, it's moving very slowly, very slowly. Turn up the power a little bit, and suddenly the arm moves. That shouldn't happen. Because the inner arm and the cart position is completely independent of each other, or pretty much independent. So I'm considering to changing. So I have one neural network for the behavior of the cart, one for the inner arm, and one for the outer arm. The outer arm will have all the information, all the state information as it has today. The inner arm and the outer arm, and the cart will have only their info. So the command for the cart will not go to the inner arm neural network, and vice versa. But yeah, it continue with this fault. And likewise, sometimes when I move the inner arm, the cart position will move. And now it's moving way too fast. Turn down the power a little bit. More power, and it moves up. Yeah, so as you can see, the model is not too shabby, but it's far from perfect. So my plan for next week is to improve this model and probably separate into 3 separate neural networks, and have a look at maybe TensorBoard, have a look into regularization techniques. Maybe I can benefit from that. And when the model is looking okay or pretty good, I will use it as an environment for DDPG.